Hi, I'm Nisha Talagala. I'm a fellow at Fusion IO. We're going to be talking about storage memory convergence, the combination of flash, technologies beyond flash, and DRAM in a hybrid memory kind of world, and the benefits that that provides.
My name is Dan Bajan, and I work at the Global Technology Ecosystem Group within SanDisk, where we manage partnerships with the big ISVs. And part of what Nisha's going to cover is the way we do software optimizations on hardware, and specifically where the market is going in terms of new hardware devices with converged memory and the software challenges that creates and how we're trying to solve them.
What we're really going to be talking about is, we've spent a lot of time talking about how do you use flash as disk, how do you replace disk, how do you do all so funky things with I/O. Really now the question is, how can you combine flash and other technologies like persistent memory kind of into the memory hierarchy? And there's 2 or 3 ways to do that. One of them is, the very first one is really to recognize that flash, even as an I/O device, has an impact on the memory in the subsystem. So, and this is something that's been known for a while. People call it by a variety of names. Some people call it DRAM displacement. Some people call it efficiency in memory, so forth. But the basic idea is, if you think about the way that applications were written, they were typically written to make use of 2 resources, DRAM and disk. And they put their persistent data in disk, and they cache it in DRAM. And how much DRAM they have depends on how much they think they need to keep adequate performance. Now, if you take out the disk and you put in a much, much faster disk, then in many applications, that means you don't need quite as much DRAM. And so the way to kind of think about that is not that your performance with less DRAM and more flash is going to get better. It's going to get more cost effective. So so that's the very first thing about kind of combining flash and DRAM, which is how do you get not just transactions but cost effective or power effective kind of transactions.
The other thing I want to point out is that flash is sort of this intersection point. What we've tried to represent here is this traditional block I/O kind of flash as disk approach on the bottom, and this newer flash as memory approach on the top. The flash devices themselves, the PCIe and SAS and SATA, play an interesting role that they can do both. The truth of the matter is there are devices that can do both on the persistent memory tier too. That's what the UltraDIMM is. The UltraDIMM can act as a block I/O device. It just sits on the DIMM slide. But what we're really talking about going forward are persistent memory devices that look and act like DIMMs. They don't necessarily look and act like a block device at all. They are simply a memory device.
So let's see, how much space would a 16 gigabyte core DIMM take up? About 40 cubic feet? Yeah, core memory. Core memory was not persistent. Core memory was persistent.
You're talking like magnetic core memory?
Yeah. I'm old, remember?
This is actually a good point. This is not the first time people have talked about persistent memories, Persistent, absolutely.
Persistent memory came around after persistent memory.
That's absolutely right. Yes, that's absolutely right.
But let's just say that. Started with drums, right?
Mercury delay lines.
Yes, that's absolutely right.
But the takeaway is that current system architecture was defined by available technology, not by actually what we would like to be working with.
Yes. That's and so as Dan kind of pointed out, what we are talking about when we say persistent memory is things that can be accessed directly by the CPU, that can be synchronously accessed and are fast enough for that purpose. They could have a variety of attach points. The attach point is not really the important thing, as long as.
So we're really talking about post-flash, byte addressable, much more symmetrical.
It includes flash. It's incorporating flash. But yes, it's
What we are talking about is the combination of byte addressable things and flash. That's really the
the other
combination
thing I
of things.
wanted to point out is you moaned at software-defined memory. But the reason why we sort of coined that term is because
virtual memory was already taken.
Well, no. That's one reason.
I was trying to remember, there was another show that was taken.
It's actually because they wouldn't let me talk about it with the term I wanted to use. So. But what we're really trying to say is that like software-defined networking, software-defined storage, this is about taking a pool of hardware devices, abstracting it with a software layer, and then allowing the applications to manage that hardware device, the software layer, in ways that make it independent of the application.
Yeah, and Dan, we offered up, Flash's memory extension, or FAME for a nice acronym. So. We already had Flash in the universe, so now we can do a Flash.
The obligatory memory hierarchy chart. Really what we are talking about is, so flash, microseconds versus milliseconds is much, much faster than disk, but it is much, much slower than DRAM. DRAM is 100 nanosecond media, and DRAM can be synchronously accessed. A modern CPU has a tolerance of about a microsecond to wait for a load of data. Anything longer and bad things happen in the CPU pipeline. And so you really can't have a CPU load to flash. That doesn't actually work. So when we talk about persistent memories, we're talking about things that are closer to that model. And when you're talking about, the point about the software-defined memories, how do you create appropriate hierarchies with now what is effectively 3 kinds of media, and that's assuming flash is 1 kind. Flash is realistically at least 2 kinds when you think about the high end versus low end and so forth. And so when we put it to a software view, it's really about, how can software best use a DRAM that is super fast, volatile, a memory that's probably not quite as fast, usually quite expensive, but non-volatile, but much, much faster than flash. In realistic cases for the next year or two, much, much smaller in capacity, and then pools of flash and then pools of HDD. And that is really, kind of some of the areas that we're working on, and I'll show you a quick impact of what it is. So when we spoke about NVMFS earlier, this is one of the reasons why NVMFS is called non-volatile memory, is that it's really not just about making it super fast, but recognizing that you could have, DRAM, that, data is resident in, recognizing that some of your files could be wholly or partially resident in a kind of media that is actually memory attachable. One of the interesting things is that file systems are the only place in the modern OS hierarchy where you can mmap to an application. So if an application wants to do a memory load to a storage device, that goes through the file system. And the file system is the one who knows where stuff is. So even if you can get really good performance at a block level from an I/O subsystem, when you try to combine persistent memories and flash, you really want to have a file view. And that has been recognized in industry bodies, activities like the SNIA non-volatile memory programming twig and so forth. And that's one of the reasons why the file system is NVM focused. So what are the implications for applications? And here I'm really only talking about implications for things that you can buy today, like an NVDIMM, small amounts of things. First thing is it enables extremely low latency transaction commits for databases. So if you have a database, for example, every database, before it can acknowledge data, it has to make sure the data is durable, which means it has to put it somewhere. And right now it's put in the log because the log is the way you can most effectively write that to some kind of storage device. But even logs to flash take tens to hundreds of microseconds. So if you have a persistent memory technology that is combined with your flash, you can actually target certain elements of your data set into the very, very low latency, high performance memory, and target the rest of it into your, relatively speaking, cost-effective flash. So those are some of the kinds of things that you can do. You can accelerate parts of your data set and so forth. You can also consider, forms of update operations or load store operations that are much, much faster than traditional I/O. So the I/O stack in most modern operating systems has been clocked at anywhere from about 5,000 CPU cycles to about 25,000 CPU cycles to perform a single I/O. A CPU memory update takes 1 or 2 cycles, or a little bit more if your latencies are longer and you have a pipeline stall when you're loading. So the efficiency of these operations is actually massive when you're doing a memory kind of operation. And so those are some of the things that become possible with these types of technologies. So something that we demoed a few months ago, which I will reiterate in this case, is now how does a database use 3 kinds of memory? And here what we are talking about is a database running on flash using an unspecified but very, very, very small amount of persistent memory. And also the normal amount of DRAM.
Just to differentiate this from our previous discussion, here's the new layer of code, or auto-commit memory layer that sits behind the file system.
And its job is to manage the cache interactions with the load store memory. The file system's job is to recognize that there are 3 resources and put appropriate parts of files in each of them. So what we demo here is essentially, like I said, 3 systems. Same hardware, 3 different software models, First is database running entirely in Flash. Second one is database running on the file system. No changes, the file system making decisions about how to use the technologies. The third one is the database recognizing that it can do memory operations to certain parts of files rather than doing I/O operations. Among other things, what this means is most applications today have been trained to think that you should not do an I/O that's not a multiple of a sector. So whatever I/O it actually wanted to do, it will find a way to create an I/O that's a multiple of a sector. And when you're doing memory operations, it can do I/O at whatever size it wanted. Which means that frequently it gets only the most important information out and it doesn't actually have to write a whole sector. That is a big difference between column 2 and column 3. In column 2, the application is talking to what it thinks is storage. We are rearranging stuff in the background. In column 3, applications are writing bytes if they want to. So generally speaking, the performance differences, and depends on the workload, of course, but if you're doing something that's write intensive, the performance differences between column 1 and 2 are about 2x. And the performance difference between column 2 and 3 is another 2x or so. And that's depend entirely on how effectively you can use these technologies. So it's not intended to replace Flash, but the point is, there are things that you can do at application level very cost effectively using technologies that are shippable today that can then take your Flash and make it that much more usable at the application level.
Okay, with technologies that are available today and a budget not equaling the GNP of most small countries, I have that non-volatile memory tier would be about 1,000th the size of the Flash tier.
And it's important to note that the baseline there was already ridiculously fast.
Yes.
A database on a Fusion IO card, not because you show like a DL380 or whatever, so people might think that that was the baseline with disks and other such archaic nonsense.
So that's a very good point, Stephen. We're comparing this to ourselves. This is coming from the Fusion IO world, where we're already PCIe, we're already close to memory, we're already as fast as you can be in terms of latency on the PCIe bus, and we're still able to accelerate significantly with this software.
And so, Howard, to your point, it's not 1,000, it's at least 100x smaller than even that.
Okay.
It's not
So think of it this way, if you have a terabyte flash card, this is not a gigabyte.
Oh, no. Because I know what that stuff costs in
Yes. So
megabytes.
Even less.
Oh, okay.
Even less. So that's the point, I think, is that, I hate to use the word software defined, but it comes down to how much you can figure out what to do with it. You don't need gobs and gobs of it.
There are lots of places where just a tiny bit.
Yes. And obviously, if it gets more cost effective, there's lots of places where lots of it helps a lot also.
Right.
But, but
This is the future world.
that's the future world.
Where, in 2025 or so, we can actually get gigabytes of something that's 1/10 as fast as DRAM and byte addressable and symmetric read-write.
And the real beauty is we're talking to developers about basically managing I/O through memory manipulation.
Right.
And you entirely eliminate really the concept of read and write. It's just...
And the nice thing, if you can get enough developers to buy into it, the nice thing is that the software will be ready when the hardware becomes cost-effective.
that's exactly.
And we won't be in the situation that we're so frequently in where here's a new hardware innovation and 10 years later we just finally figured out how to use it.
And that's actually exactly right, which is there are things that you can do with things, with media that's cost effective today, which are very, very small capacities that are architecturally and structurally identical to what you would do with the larger technology that may or may not show up.
You can get, megabyte, small number of megabytes of MRAM or STT-RAM that, it's really in production and it works well enough that you wouldn't worry about if it's going to be...
Well, I actually think this is another key to what we're trying to accomplish, because although we recognize that we can get out in front of the curve in terms of software development and evangelization, we're not going to move the entire enterprise data center to flash-aware software soon enough. So we're taking that both transparent and non-transparent approach. In the transparent case, what is transparent is that the application up stack doesn't know that it's talking to a different I/O. It simply reads and writes a file like it always has, and all the optimizations happen transparently behind the scenes. Non-transparent is what we want, which is applications become aware that they're talking to a more intelligent I/O stack, and they're modified to take advantage of that, and that's when you see the really significant performance.
And one thing to also note is that even when we're talking about non-transparent and the application being aware, that doesn't mean that their management utilities or their backup utilities or anything else has to be aware. So one of the nice things about integrating properly at a file system level is anybody can come along and do I/O anytime they want, and they will always get the correct data. The only application piece of code that needs to be aware is your primary app if it wants to be. So your management model stays pretty much identical, and your database can do load, store to persistent memory. Your backup application can still read the file and use any utility it used before.